This video is for the revision of sigma bonds, pi bonds, and hybridization. Okay, for a covalent bond to be formed, let's say I'll draw a methane here. Carbon has 4 outermost electrons, and hydrogen, each one I'll draw a dot for it. So they share electrons here. For this covalent bond to be formed, their orbitals must overlap. Okay, there are two types of overlap here. If it overlaps at the end, so end on, like how I draw here, then it's a sigma bond. Okay, other examples, if I were to draw it this way, it's fine. And let's say I put an s orbital here. So this s orbital and this p orbital. So this is still at the end of the p orbital. So it's still end on. So it's still a sigma bond. So this is a sigma bond. This is a sigma bond. I can draw it differently this way and put my s orbital here. It's still a sigma bond. Pi bonds are weaker because they overlap less. So if we look at this overlap here, this way, so it only overlaps this small space here. So there's less overlap compared to a sigma bond. So if it overlaps sideways, then this overlap is a pi bond. So it's weaker than a sigma bond. Originally, the p orbital, before any hybridization, we imagine this x-axis, y-axis, and z-axis, and the p orbitals are just on the axis, x, y, and z is going into my page and out of my page. So all 90 degrees from each other. Now this is the original p orbital, and the s orbital is just there. So it has lower energy level. The s orbital has lower energy level, and the p is slightly higher. If we show the energy level, then we can see that, oh, 2s is slightly lower than 2p, 2p, and 2p, so x, y, and z. Remember, we always fill in the electrons, first singly, then in pairs, for the lower energy first. When they're all fully filled, then we go to the next energy level, and we go single, single again. Okay, this is before it was hybridized. When it's hybridized, the electron in the s orbital will be promoted to the p energy level. And if we look at this new arrangement, all of them looks the same. So there's one electron in this 2s, one in the 2p, 2p, 2p. They all become the same energy level, and they look exactly the same now, which means it's something like mixing this 4 together, mix it up and divide it back to 4. So now each of them has one electron and they're all identical. We don't know which was the s orbital and which is the p orbital anymore. So that is why we draw them same energy level like this. Now what about their shape? So originally we know that s orbital looks like this, spherical. And then px orbital, I'll draw one like this, and py and pz. So originally there's 1, 2, 3, 4. Now can you imagine all 4 of this orbital got mixed up and I divide it to 4 again like this. So it ends up to become this shape. It looks kind of like your tetrahedral shape. So it was divided to 4. So at first it was this spherical, and then the dumbbell, and another dumbbell, all mixed together and divide to 1, 2, 3, 4. This we call the sp3 hybrid. So in the methane just now, there's no difference between this electron and this electron and this electron and this electron. They're all identical. They don't have like different energy level. They look totally identical to chemists. So they come up to the conclusion that they're all the same level. And it's all part of this 1, 2, 3, and 4. That is why methane holds that shape 1, 2, 3, and 4. So that's why tetrahedral shape. So if we're drawing a methane, the H is its s orbital that is overlapping the p orbital or sp3 orbital from the carbon, right? So hydrogen doesn't have a p orbital. So we know that s orbital is spherical shape. So it looks like this. Overlap, overlap, overlap. So this is the carbon, and this is the hydrogen, 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 and hydrogen. Since it's the ends that overlap, so these are all sigma bonds. Sigma, sigma, and sigma. Now let's look at this one. This is two carbons. So this is probably an ethane. So two carbons here, both has that tetrahedral shape. And you see that the end of that tetrahedral is going to overlap the end of this tetrahedral. So they meet ends on again. So this is also a sigma bond. So when these overlaps, they're all gonna form sigma bonds. Sigma, 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 and sigma, sigma, sigma bond. So the basic shape here would be tetrahedral. So this is just the basic shape. So it includes all the other shape that is under tetrahedral. Next, sp2 hybrid. sp2 hybrid, two here means that there's only two of the p orbitals are involved, whereas just now all of the p orbitals were involved in the hybridization. So in this case, one of the s and two of the p, they join together. So all three of this, the spherical, the dumbbell, and another dumbbell, and there's another dumbbell that didn't join them. So all of these, you mix them together, mix, 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 and divide it back to 3. So originally they would look something like this from the top view. Okay, so that would be this view. So say our eyes are here. If we look to the bottom, so it's like 1, 2, and 3. It actually looks like this from the top. This is probably an ethene. So C, 1, 2, H, H, one of it, H, and another H. So when two of these overlap, the ends will overlap first. So when these overlap, again, it's a sigma bond. And the H overlaps here and here, and the other one as well. So this is sigma, 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 sigma. But don't forget, there's one more that didn't join the hybridization. That would be the 2pZ. So this one didn't join the hybrid, right? So it's still in its original shape, that dumbbell. So that dumbbell is still there. We didn't do anything to it. Okay, so when these overlap, it will overlap this way, like how we drew up there. So just a little bit of overlap like that. That is the pi bond. So when there's a double bond, then it's a pi bond. So the basic shape for this, so you see that this is 1, 2, 3 bonded pairs. It would be 120 degrees, which means this is a trigonal planar, as in the basic shape. What would the sp hybrid mean? So it means one of the s and one of the p hybridize. So leave the other two p orbitals alone. So these two are not going to join a hybrid. These two are going to be mixed together and divide to 2 again. So it becomes like a really huge dumbbell like this. So this is one carbon, a really huge dumbbell, and this is the hydrogen. So when they overlap, it's the ends overlap, therefore a sigma bond. And here, the hybrid and the other hybrid overlaps also at the end. So another sigma bond. This also the end, and from the H, when they overlap, it's a sigma bond. Okay, but don't forget there's 2 more that is the original self, the original p orbitals. So one of the p orbitals is this way, and the other p orbital is going into the page and out of my page. So same here, and into my page and out of my page. So when they go near to each other, this side and this side will overlap. Here and here is going to overlap. And the one that's in the page and out of the page, this side of it will overlap with the other side of this. And then this side is going to overlap with this. So it's also the sideways and not the ends. So two of these are pi bonds. So that is actually an affine, which shows that there is a sigma bond here, sigma, pi, and pi. The basic shape for this would be linear, as in 180. Next, which bonds are sigma and which are pi? So let me redraw this. We open up all the bonds to see whether they are sigma or pi. In exams, if you want to check your structure, just make sure all your carbons has 4 bonds. All your hydrogens have only 1 bond. If there's an oxygen, it should have 2 bonds. And if there's nitrogen, it should have 3 bonds. For example, I should know that this carbon here should have another 2 hydrogens because it should be 1, 2, 3, 4. So 4 bonds. And this carbon, for example, 1, 2, 3, 4. So all the single bonds here would be sigma bond, sigma, sigma, all of them sigma, sigma. All of the single bonds are sigma, but let's look at the double bond. So we learned just now that if it's a double bond, the first one would be sigma, and the next one would be pi. And let's move on to the other side. So sigma, pi. All these are sigma, sigma, all the single bonds are sigma. And this one, sigma, pi, and pi, sigma. So all the single bonds here, they are sigma bonds because they overlap at the end. Or it could be 1, 2, 3, 4, and the end. So they are all sigma bonds. But if there's a double bond, it'll be a sigma pi. And if it's a triple bond, it'll be a sigma pi and pi. Let's see what overlap is this bond. So this carbon has 4 bonds, so it looks like this. So that is sp3. So it's the sp3 overlapping the S from the H. So it's an sp3 overlapping an S for that bond. What overlap is this? So since it's 1, 2 bonded pairs like this, as in like they're linear, so its hybrid is a super huge sp here. It looks like a huge dumbbell because it's a hybrid between the S and the P. So the carbon sp here and the other carbon sp. So this overlap is sp to sp. What about this carbon to this hydrogen? So the overlap is from sp to the s orbital from the hydrogen. So sp with s. What overlap is this? So there's 1, 2, 3. So it should look like this. That is the sp2. So the overlap here would be sp2 to another sp2. And what about this bond? So we know that this is 1, 2, 3. So this is again sp2. So sp2, and for hydrogen, it's the s orbital. So sp2 to s overlap. So those with basic shape of tetrahedral, they overlap sp3. Okay, so we saw that methane was an sp3. So this is a methane, but not forgetting things like ammonia. So we know ammonia is 1 lone pair and 3 bonded pairs. So its basic shape is still the tetrahedral. So it's also sp3. Don't forget that. So the shape goes something like this. It's just that nothing's overlapping up there, but this is still sp3 towards the S of the hydrogen. So there's no overlap only up here because it's a lone pair. Anything trigonal planar, they overlap by sp2. So we saw ethene just now. So 1, 2, 3, and then there's the hydrogen. So BF3 here also 1, 2, 3, and one of the p orbital is probably empty. Okay, how do we draw NO2 minus? N has 5 outermost electrons, O usually with a double bond, and if it has a charge, usually a single bond. O has 6 electrons. 1, 2, 3, 4, 5, 6. 1 extra for that negative. And nitrogen 1, 2, 3, 4, 5. So it has 1 bond pair, 2 bond pair, 1 lone pair. So the original shape is also trigonal planar. So the orbital looks like that, which means it is also sp2 on the nitrogen, just that this part is not overlapped with anything. Sp is for anything linear. So besides ethine, other examples, something linear. Carbon dioxide is linear, so it's also the sp overlap. So they look like a huge dumbbell and another huge dumbbell, s orbital, the s orbital, and the two p's will overlap by pi. So it's the sp overlap, and this will be an sp as well. Don't forget that the real shape of ammonia is actually trigonal pyramidal, although we put it under tetrahedral as its basic shape. Also for NO2, it's actually a V shape or a non-linear, but we put it under trigonal planar for its basic shape.